Okay, welcome back dear students to the tutorial about the group theory. In the previous videos, we had discussed about the fundamentals of group theory, especially the character table, how to construct a character table, and reduction of a reducible representation into irreducible representation like that. And from this video onwards, we will discuss about the chemical applications of group theory. We know that there are several applications for group theory for the construction of molecular orbitals and in the field of coordination chemistry, especially the ligand field theory like that, and in the spectroscopy. And there are very vast areas in which group theory can be applied. And one of the important area is spectroscopy. That is especially the IR, Raman, and UV spectroscopy. Okay, that is using group theory, we can find out the possible modes of vibrations of a molecule and which modes will be IR active or Raman active, like that can be predicted using group theory. So one of the very interesting areas of group theory. Okay, we can find out the transition probabilities of infrared and Raman spectroscopy. Okay, first we know that for a molecule there are 3n modes of degrees of freedom. There are 3n degrees of freedom for a molecule containing n atoms. A molecule having n atoms, there will be 3n degrees of freedom. Okay, and out of these 3n degrees of freedom, 3 are translation. That is translation of the center of gravity of the molecule in the xyz direction. Translation in the xyz direction. And the other three are rotational freedom, rotational motion. Okay, and therefore the vibrational degrees of freedom will be 3n minus 6. Okay, vibrational degrees of freedom will be 3n minus 6. And for linear molecule, it will be 3n minus 5 because rotation about the molecular axis is not considered. It is actually the translation itself. So in the case of linear molecule, there will be only 3n minus 5 vibrational degrees of freedom. Okay, and you may be studied that only vibrations with change in dipole moment is infrared active. Suppose I think you have studied in the UG level that in the spectroscopy, that is only those vibration which are in which there will be a change in dipole moment is infrared active, IR active. Okay, and Raman activity is associated with the polarization of the molecule. Okay, only vibrations which brings about change in polarization will be Raman active. Okay, so for IR active there should be change in dipole moment. For Raman activity there should be change in polarization. Okay. Okay, the first step in the prediction of vibrational modes, okay, is the calculation of total character. Okay, calculation of total character is the first step to determine the normal modes of vibration and its symmetry. Okay, symmetry of the normal modes of vibration. For the determination of the symmetry of normal modes of vibration, first thing is calculation of total character. This can be done in this way. There is the 3 degrees of freedom, 3 degrees of freedom of each atom in a molecule may be represented by 3 mutually perpendicular arrows, x, y, z. Okay, that is each atom has 3 degrees of freedom, and that is represented by the Cartesian coordinates or the 3 vectors x, y, z. And these 3n vectors may be taken as the basis for evaluating the total character. Okay, that is for each atom we are fixing 3 vectors x, y, z. Parallel, that is all x are parallel to each other and all y are parallel and all z are parallel. And there will be 3n vectors. And that makes the basis for calculate the total character or total character. That will be a reducible representation. Okay, clear. I think you may be more clear while discussing the examples. Okay, we can move on. If we subtract the characters relating to the translational and rotational degrees of freedom from the above total character, we will get the character relating to the vibration degrees of freedom. That is first we are constructing the total character, and that total character include all the degrees of freedom, all the 3n degrees of freedom, and from that we are subtracting the translation degrees of freedom and rotational degrees of freedom. Then we will get the vibrational degrees of freedom. And for this we take a simple molecule, water as example. Okay, we can take water as the example. And the point group of water is very simple, C2V. The elements are E, C2, sigma V and sigma V dash. Okay, elements of the C2V point group are identity operation C2 layer, sigma V, actually sigma V XH plane, and sigma V dash, that is sigma V in plane in the YZ plane. And the basis vectors are x1, y1, z1, that is here. This is x1, y1, z1 for this hydrogen, x1, y1, z1, and this is oxygen, x2, y2, z2, and for hydrogen x3, y3, z3. And these 9 vectors is the basis for the representation we are going to determine the total character, total representation. Okay, and the transformation of these vectors gives a 9-dimensional matrix. We get a 9-dimensional representation or 9-dimensional matrix. During the operation, the vectors x1, y1, z1, etc. changes to x1 dash, y1 dash, z1 dash, etc. So we can write an equation like this. That is, we get a transformation matrix here. Okay, and the basis vectors are x1, y1, z1, etc. Last x3, y3, z3, and that is equal to x1 dash, y1 dash, z1 dash, etc. z3 dash, and this is a matrix equation. Okay, so we want to construct this transformation matrix. We find out the transformation matrix. So okay, first consider the operation E. Okay, in operation E, all the vectors are retained. That is x1 dash is equal to x1, y1 dash is equal to y1, etc. Okay, during operation E, if we carry out operation E on this water molecule, okay, all the operations, all the vectors will be retained. Okay, then the matrix will be a diagonal matrix. Okay, diagonal unit matrix. Okay, therefore the character, we get a 9-dimensional unit matrix. All the non-diagonal elements are 0, only diagonal elements are 1. Therefore, character of E is equal to 9. Character of E is equal to 9. And that is for operation E. And for C2 operation, okay, what will happen for C2 operation? Look here. Okay, C2 axis passing through the oxygen. Therefore, all the vectors of hydrogen and these two hydrogen are exchanged. That is, x1 become minus x3 and y1 become minus y3. Z1 is equal to z3. Okay, and this z2 is equal to z2. Y2 is equal to minus y2 during rotation by 180 degree. Y2 become minus y2. X2 become minus x2. Okay, you can see here. That is, x1 is equal to x3 dash. Y1 is equal to minus y3 dash. Okay, sorry, x1 is equal to minus x3 dash. Y1 is equal to minus y3 dash. Z1 is equal to z3 dash. Okay, x2 is equal to minus x2 dash. Y2 is equal to minus y2 dash. Z2 is equal to z2 dash. Okay, that is, in x2, y2, z2, the vectors remain same. Only the direction changes. Okay, while x1, y1, z1 and x3, y3, z3, both direction and the position is changed. x3 is equal to minus x1 dash. Y3 is equal to minus y1 dash. Z3 is equal to z1 dash. Okay, so the matrices look like here. Only the x2, y2, z2 characters are present in the diagonally. All others are non-diagonal. Okay, transformation of x1, y1, z1 changes their position. x1 become minus x3 dash. Okay, x1 is equal to minus x3, therefore minus of x3. Y1 is equal to minus y3. So these characters come here, not in the diagonal. And similar, the x3, y3, z3 transforms as x1, y1, z1. Therefore, this come here. Only x2, y2, z2 come in the diagonal. Therefore, character of C2 is equal to minus 1. Okay. Now consider the matrices for sigma v xz. Okay, which is sigma v xz plane? Okay, we can look back. Okay, sigma v xz pass through pass through like this. This is the plane. Okay, therefore, in this case also, Z2 and X2 retain. Okay, Z2 and X2, no change in position and no change in direction. Y2 position doesn't change, but its direction opposite, become minus Y2. And all X1, Y1, Z1, X3, Y3, Z3 exchange each other. Therefore, they will not come in the diagonal. So they are not participate in the character of the matrix. So that is not important. Only the vectors, that is position remains retained, contribute the character to the matrix or the operation. So x3, y3, z3 no contribution to the character. Only x2, y2, z2 contribute the character. We can see here. Okay, as I told you, x1 is equal to x3 dash, y1 is equal to minus y3 dash, z1 is equal to z3 dash. Position is changed. In the case of y1, both position and direction changed. But x2, y2, z2 position retained. x2 is equal to x2 dash, same, no change in direction and position. Y2 is equal to minus y2 dash, position change retained but direction opposite. Z2 is equal to z2 dash. So only these three will be in the diagonal elements. Only the y become minus 1, x and z is equal to 1. Therefore, character is equal to, character of sigma v is equal to 1. Okay, and similar way, sigma v dash, actually sigma v dash is sigma v yz, And which is that plane? We can look back to our example. Okay, this is our example. In this case, the plane is the YZ plane is this is the Y axis, this is Z axis. Therefore, this molecular plane. Okay, so all the vectors, their positions are retained. All the vectors positions are, so all contribute to the character. And the YZ plane, so Y and Z, okay, their position and direction will not change because YZ plane is in the YZ plane. Okay, sigma V dash. Only X vector changes its sign. So all the character of Y and Z are 1 and all the character of X is will be minus 1. Okay, we can see here the X minus 1, Y1, Z1. Again X2 minus 1, Y21, Z21, X3 minus 1, Y21, sorry, Y31, Z31. So character is equal to, okay, 3 minus 1, 6, 1. So 6 minus 3 is equal to 3. Character of sigma V dash is equal to 3. Okay. Thus the total representation taking the 9 vectors on 3 atoms on water as the basis is the character of E is equal to 9, character of C2 we get minus 1, character of sigma V we get 1, character of sigma V dash we get 3. So 9 minus 1, 1, 3. That is the representation. Actually it is a reducible representation, gamma reducible. It's a total representation. It is a reducible representation. Okay. And this is the direct method to obtain the total representation. And there is another easy way. That is in these examples we can see that only the atoms which retain its position contribute to the character. Okay, only that atom which retain position contribute to the total character. In such atom, each vector which retain direction also contribute 1 and each vector which reverse direction contribute minus 1. Understand? Okay, that is each vector which retain position contribute 1. Both position and direction contribute 1 and the vector which retain position and reverses direction contribute minus 1. So total character we can form an equation. Number of atoms retaining position. Number of atoms retaining position into number of vectors retaining direction minus number of vectors reversing direction. Okay. Number of atoms retaining position into number of vectors retaining direction minus number of vectors reversing direction, because number of vector retaining direction character is 1, so it is plus. Number of vectors reversing direction is minus 1, so it is minus 1. So equation is this: chi r, total representation chi r is equal to nr into a minus b, where nr is the number of atoms retaining its position during the operation. A is the number of vectors which retain direction, and B is the number of vectors which reverse the direction. Okay. For example, in the case of operation E, number of atom retaining position n is equal to 3. All the atoms retain their position and all the vectors also retain their direction. Though there is E operation, all remain same, there will be no change. Therefore, A is equal to 3, B is equal to 0, N is equal to 3. So 3 into 3 minus 0, NR into A minus B. A is equal to 3, B is equal to 0. So it is 9. In the other method also we get 9. Same thing, no change. C2. C2 passing through oxygen. Only oxygen retain position. Because in the case of C2, this is water molecule. C2 axis passing through oxygen. So only oxygen retain position. and C2 is actually C2Z. Okay, so only Z coordinate retain direction, X and Y reverse direction. Therefore, N is equal to 1 and vector in the Z direction retain direction. So A is equal to 1, X and Y reverse direction. So B is equal to 2. So chi C2 is equal to 1 into 1 minus 2. That is minus 1. So, the other case, sigma V XZ. Sigma V XZ is actually this plane. This is sigma V XZ. In this case also, this plane passing through oxygen. So only oxygen retain position. The plane is XZ plane. Therefore, X and Z retain direction. Y reverse direction. So passing through oxygen atom. Therefore, N is equal to 1. Number of atoms 1. Only Y vector reverse. Therefore, B is equal to 1, A is equal to 2. So, chi sigma V is equal to 1 into 2 minus 1 is equal to 1. Okay. And sigma V dash YZ. Sigma V dash YZ is actually, okay, sigma V dash YZ plane is this one. This plane, that is a molecular plane. Therefore, all the atoms retain their position. Therefore, N is equal to 3. Pass through all atoms. And YZ plane, therefore Y and Z retain its direction. So A is equal to 2. Only X coordinate reverse direction. B is equal to 1. So 3 into 2 minus 1. That is equal to 3. Okay. So the characters are 9, minus 1, 1, 3. And that's we already got in the other method also we got the same thing. That is 9 minus 1, 9 minus 1, 1, 3. Okay. But there is a problem in this shortcut method. If the order of the axis of rotation is greater than 2, this method fails, since it is not easy to identify whether a particular vector reverse direction or not. Okay, for example, in the case of C3 operation, we cannot say directly X and Y reverse direction or not. It's very difficult. In case say C4, C5, etc. In such a case, we can use a more general method. In this method, all operations of a group will be classified either as a proper rotation or improper rotation. All the operation, plane of symmetry and all operations are considered as classified as a proper rotation or improper. For example, the E can be written as C1, a proper rotation, okay, by an angle of 360 degree. And I is, we have already studied, I is equal to S2, an improper rotation by an angle of 180 degree, S2. I is equal to S2. S2 is an improper rotation. And sigma also we can write sigma into C1. Okay, C1 is actually E. C1 is E. Sigma into E is sigma itself. So sigma into C1 actually S1. Okay, so the sigma operation, the plane of symmetry can be written as an S1 operation. Okay, improper rotation. We know that only those points which retain position will contribute the character. That we have already studied. Only those points which retain position will contribute the character. And contribution of one point is, we have studied in the case of proper rotation, the character is 1 plus 2 cos theta. Do you remember? Like in the case of proper rotation, the character of the matrix is 1 plus 2 cos theta. And for proper rotation, and for improper rotation is minus 1 2 cos theta, or 2 cos theta minus 1. Okay, for proper rotation the character is 2 cos theta plus 1. For improper rotation it is 2 cos theta minus 1 for improper rotation. Thus the total character of an operation R can be written as chi R is equal to NR into, NR is the number of atoms retained position, into plus or minus 1 plus 2 cos theta, or 2 cos theta plus or minus 1. Okay, that is the equation to calculate proper rotation in a more general method. in the case of, it is more, it can be used in the case of there is a proper rotation having order greater than 2. Okay, we can apply this equation to C2V point group of water. Okay, C2V, the elements are E, C2, sigma V dash. Theta is equal to, in the case of E, theta is equal to 0 degree. Theta E is equal to, we can write it as C1, therefore is 0 degree. C2 is 180 degree. Angle is 180 degree. Sigma V, the angle is 0. Okay, sigma V, we are taking it as actually these two are proper rotation, these two are improper rotation. Okay, I already told you sigma V can be written as sigma V into C1, that is S1. Okay, therefore C1 means rotation by 360 degree or 0 degree. Okay, so it is 0 degree, sigma V dash is 0 degree. So cos theta, we know cos 0 is equal to 1 and cos 180 is equal to minus 1. Cos 0 is equal to 1, cos 0 is equal to 1. Plus or minus 2 cos theta. Here, these two are proper rotation, therefore plus sign. These two are improper rotation, sign is minus. Okay. Therefore, it is 1 plus 2 into cos theta, cos 0. That is 2. 1 plus 2 is equal to 3. And here it is 1 plus 2 cos theta. Here cos theta is equal to minus 1. So 1 minus 2 is equal to minus 1. Here 2 cos theta minus 1. 2 cos theta minus 1. Open 2 minus 1 is equal to 1. Here also 2 cos theta minus 1 is equal to 1. And NR, that is number of atoms retaining their position. In the case of E, it is 3. C2 only oxygen retain position. Sigma V also only oxygen retain position. Sigma V dash, all the 3 atoms retain their position. Therefore, gamma is equal to NR into plus or minus 1 plus 2 cos theta. About 3 into 3, 9. 1 into minus 1, minus 1. 1 into 1, 1. 3 into 1, 1. 3. Okay, again we get the same result. That is, characters are 9, minus 1, 1, 3. Already we got this in the other two method also. Okay, we can use any method. Okay, this is a more general method. I think the second method is more useful if we use in the case of C2V like that. But in the case of proper rotation having angle greater than 180 degree or order of greater than 2, then that may make some problem. In that case, you can use this equation, that is gamma is equal to NR into plus or minus 1 plus 2 cos theta. It's a very general equation. We can easily construct the total character. Okay. So we get the total character. And next step is to, the total character is actually, this is our total character. This is actually a reducible representation. So next step is to reduce it into irreducible representation. This is a total character. Okay. And this is the character table for C2V. Using the character table of C2V, reduce this total character, which is a reducible representation, into irreducible representation using our reduction formula. What was reduction formula? Reduction formula is equal to NR is equal to 1 by H into chi R into chi R. Do you remember? This is our equation. Chi R, 1 by H into chi R into chi R. Also GI is there, number of elements. Okay, so NA1, that is number of times A1 representation present in this reducible representation, is equal to 1 by, here H is equal to 4, 1 by H is equal to 4, into GI in the all cases 1, number of elements in all classes here 1. So 1 into chi R, 9 into 1. Okay, here also 1 into minus 1 into 1. Okay, this is equation. We have already discussed this one. So we get 3. Similarly, NA2, using the reduction formula 1 by 4, 1 into 9 into 1, 1 into all this, 1 into minus 1 into 1, 1 into 1 into minus 1, 1 into 3 into minus 1. Okay, in this case we get 2. Okay, n b1, similarly 1 by 4 into 1 into 9 into 1, okay, 1 into minus 1 into minus 1, okay, 1 into 1 into 1, 1 into 1 into 1, b1, so okay, 1 into 1 into 1, okay, 1 into minus 1 into 3, minus 1 into 3, this is 2. Okay, similarly n b2, 1 by 4 into 1 into 9 into 1, 1 into minus 1 into minus 1, 1 into minus 1 into 1, okay, 1 into 1 into 3, 1 into 1 into 3, that is 3. That is number of times A1 present in this total representation is 3, that is 3A1. Number of times A2 present in this total representation is 1, therefore A2. Number of times B1 present in this total representation is 2, so 2B1. And number of times B2 present in this total representation is 3, therefore 3B2. So this total representation can be reduced into irreducible representation, that is 3A1 plus A2 plus 2B1 plus 3B2. So these are the 9 degrees of freedom. 9, 3 plus 1, 4 plus 2, 6 plus 3. These are our 9 degrees of freedom. Okay, from this total representation we get 9, the all degrees of freedom, and that will be the basis for the irreducible representation. So okay, so we get the total representation gamma is equal to 3A1 plus A2 plus 2B1 plus 3B2. And it includes all the 9 degrees of freedom. This is the all 9 degrees of freedom. This include translational, rotational and vibrational degrees of freedom are included in this. So if we subtract translational and rotational degrees of freedom, the remaining will be vibrational. That is the second step. Okay. Okay. From C2B character table, translational degrees of freedom in XYZ direction transforms as B1, B2, A1. Okay, that is, look at the character table, X, Y, Z. X transforms as B1, Y transforms as B2, Z transforms as A1. That is, translational degrees of freedom in the X direction is B1. Okay, and in the Y direction is B2, Z direction is A1. Okay, so translation degrees of freedom are actually B1, B2 and A1. That is gamma translational. And rotation degrees of freedom Rx, Ry, Rz are the rotational coordinates. Okay, and they transforms as Rx transforms as B2, Ry transforms as B1, Rz transforms as A2. That is actually B2, B1, A2 are the B2, B1, A2 are the gamma rotational. Okay, that is translation degrees of freedom are B1, B2 and A1. Rotation degrees of freedom are B2, B1, A2. And that is given here. That is X, Y, Z direction transforms as B1, B2, A1 respectively. And rotation degrees of freedom Rx, Ry, Z transforms as B2, B1 and A2 respectively. So gamma translational is A1, B1, B2. Okay, A1 is X transforms as X, that is translation degree in the X direction. B1 in the Y direction, B2 in the X direction. And rotational, okay, this is RZ, rotation in the Z direction. So rotation freedom. Okay, this is R Y, this is RZ. Okay, so the okay, the translation degrees of freedom are A1, B1, B2. Rotation degrees of freedom are A2, B1, B2. So this is our total character 3A1, A2, 2B1 plus 3B2. By subtracting translational and rotational degrees of freedom, we get vibrational degrees of freedom. So 3a1 minus a1, we get 2a1. a2 minus a2, that is not come here. 2b1 minus b1 minus b1, that is cancelled. 3b2, b2, b2, only one b2 left. Therefore, vibrational degrees of freedom are 2a1 plus b2, 2a1 plus b2. Okay, so our vibrational degrees of freedom or the vibrational symmetry corresponding to vibrational degrees of freedom means symmetry corresponding to vibrational degrees of freedom are 2a1 and b2. Okay, that is gamma vibrational is equal to 2a1 plus b2. Others are rotational and translational. That means that out of the three vibrations of H2O, 2 transforms as A1, 2A1. 2 vibrations transforms as A1 and 1 vibration transforms as B2. 2 vibrations transforms as A1, 1 vibration transforms as B2. That means 2 vibration becomes the basis for A1 symmetry or A1 representation, A1 IR, and 1 vibration becomes the basis for the B2 symmetry or B2 irreducible representation. Okay, we know that water molecule, the number of vibrations is 3. Okay, there are 3 atoms, therefore 3 into 3, 3 and minus 6, 3 into 3 minus 3, that is 9 minus 3 is equal to 9 minus 3 is equal to 6. Sorry, there are 3 3 and minus 3 atoms. Sorry, 3 and minus 6, no, 3 and minus 3, 3 and minus 6, therefore it is equal to 3. So number of vibrations in water molecule is 3. And these 3 vibrations have symmetry 2A1 and B2. That is 2 vibration transforms as A1, 1 vibration transforms as B2. And we want to find out which vibrations are these corresponding to this symmetry. That is 3 vibration modes of H2O are, we know that one is symmetric stretching, another one is asymmetric stretching, and third one is symmetric bending. You might have studied this one in the UG classes. In water molecule there are 3 modes of vibration. This one is symmetric stretching. This is an equilibrium position, and it's both the bonds elongate in the same length. Then again equilibrium position. They both the bond contract in the same distance. There may be a mistake in my drawing, but it is same length. Okay, it is an equilibrium position. Okay, and this is the symmetric stretching. It is nu 1. Its frequency is nu 1. Okay, and what is the symmetry of the symmetric stretching? Okay, if you consider all are symmetric, therefore in the case of all the operation transforms in this any one of these, no change in orientation. Okay, that is C2. If we apply C2 here, we get the same configuration, no change. Okay, in the case of this also C2, no configuration change. Similarly, in the case of sigma V, no change. Here also sigma V, no change. Sigma V dash. There is no change in the orientation in all the operation. So the characters will be all the elements will be 1. Therefore, the characters for, I can show here. Okay, that is symmetric stretching mode. In the symmetric stretching mode, orientation is retained by all symmetry operation. So the characters is 1, 1, 1, 1, and that is A1. That is symmetric stretching transforms as A1. That is this new one, that is symmetric stretching mode is actually A1 symmetry. This symmetric stretching is having A1 symmetry. And asymmetric stretching. In asymmetric stretching, if we apply E operation, there will be no change. Therefore, character is 1. But C2, if we apply C2 here, it become this long bond become here, short bond become here. Therefore, it look like the other extreme, this one. Okay, that means its orientation become reversed. Therefore, character is -1. In sigma v this bond, sigma v also this long become short, short become long. That is the orientation is shifted. Therefore, again character is -1. In the case of sigma v dash, that is this molecular plane. In that case, there will be no change. Therefore, character is 1. So the characters are 1, -1, -1, 1. Look at the character table. Okay, look at the character table. The characters we got 1, -1, -1, 1. That is B2. Okay, that means the asymmetric stretching vibration has symmetry of B2, or asymmetric stretching transforms as B2, or asymmetric stretching is the basis for the B2 irreducible representation. In the case of symmetric bending, all are symmetrical. Therefore, all the orientation will remain same. These characters will be 1, 1, 1, 1. Therefore, it is also A1 representation. Okay. So, symmetric stretching is A1. Symmetric bending is also A1 symmetry. And asymmetric stretching has B2 symmetry. Okay. So, okay, you can see here, in the case of asymmetric stretching, symmetry is retained. So in the case of E operation, symmetry character is 1. C2 changes the orientation as that of the other extreme, and hence the character is -1. Sigma V XZ orientation changes, character is -1. Sigma V dash YZ orientations are equivalent, character is 1. Characters 1, -1, -1, 1 are those of B2. That is, anti-symmetric stretching transforms as B2. Okay, then symmetric bending, orientations are retained by all operation. Characters are 1, 1, 1, 1. That is, it belongs to A1. That is symmetric bending. That is, we have studied that. I am concluding. First, we have constructed the total character. Okay, by applying Cartesian coordinate on all the atom. Okay, then we get a reducible representation, and that is the basis for 3n degrees of freedom. Now it is reduced into irreducible representation. From this character table, we can find out which are the translation degrees of freedom and which are the rotation degrees of freedom. What is very simple. Translation degrees of freedom are x by z. The symmetry corresponding to x by z are the translation degrees of freedom, and symmetry corresponding to Rx, Ry and Rz are the rotation degrees of freedom. From the total representation, subtract gamma translation and gamma rotation, we get gamma vibration. And from this vibration degrees of freedom, we have to assign which vibrations have which symmetry. Okay, in the case of water molecule, symmetric stretching, we have find out that it is A1 symmetry. Asymmetric stretching, it has B2 symmetry. Symmetric bending, A1 symmetry. Okay. In the next video, we will discuss out of these vibrations. So we have find out vibration. What is the symmetry of the vibration? Degrees of freedom of water molecule. Our next step is which of these vibration will be IR active and which vibration will be Raman active. That we will discuss in the next video. Okay, thank you for watching. Thank you.